You're looking at a city built from 220,000 cubic yards of solid ice, structures reaching heights of 160 feet, entire replicas of world landmarks carved down to the millimeter, and every single piece of it constructed in 21 days by 10,000 workers operating in minus 40-degree temperatures. China doesn't just build an ice festival. They engineer a frozen metropolis larger than 80 football fields, using construction techniques that shouldn't even be possible with a material that melts. This is how they turn a frozen river into architectural marvels that weigh thousands of tons, all before the clock runs out. Here's how they engineer the impossible. When failure means everything melts. The ice harvest. The construction starts on the Songhua River in December, when the ice reaches exactly 5 feet thick. Not 4 feet, not 6 feet. 5 feet of perfectly frozen water is the only specification that works for what comes next. Engineers drill test cores every 6 hours, measuring density and structural integrity, because if the ice isn't uniform all the way through, entire buildings will collapse during assembly. You need ice so clear, you can read through it, with 0 air bubbles, 0 impurities, and a compression strength of over 1,000 pounds per square inch. Then, the chainsaws come out. 20 crews work simultaneously across a 2-mile stretch of river, cutting blocks that weigh up to 1,500 pounds each. These aren't random chunks. Every block is cut to exact dimensions: 6 feet long, 3 feet wide, 5 feet deep. You're watching industrial mining operations on a frozen surface, with workers standing on ice while cutting through ice, knowing that one miscalculation means the entire section breaks apart and sinks. They harvest 18,000 blocks in the first 72 hours alone. But here's where the engineering gets insane. The ice can't warm up, not even 1 degree. From the moment a block is cut, it has a 4-hour window before temperature fluctuations create internal fractures. Every single block needs to travel from river to construction site, get sorted by size and clarity, and reach its designated structure before microcracks form. You're moving 220,000 cubic yards of ice on a countdown in conditions cold enough to freeze diesel fuel in the trucks. And they haven't even started building yet. The construction army. 10,000 workers mobilize on site the moment the first ice blocks arrive. You're not looking at casual laborers. These are specialized teams, ice sculptors who've trained for decades, structural engineers calculating load distributions in real time, crane operators moving 1,500-pound blocks with millimeter precision, and welding crews working with a material that shatters if you breathe on it wrong. Every single person operates in 3 8-hour shifts around the clock, because the construction window is 21 days and there are no extensions. The temperature never rises above minus 20 degrees Fahrenheit. That's not a weather condition. That's a requirement. If the air warms up, the ice mortaring technique fails completely. Workers spray water between ice blocks, and it needs to freeze solid in under 90 seconds to create structural bonds. You're watching construction crews in extreme cold gear, handling ice bare-handed because gloves reduce precision, knowing that exposed skin freezes in under 2 minutes. They're building structures 15 stories tall using a building material that exists in a 6-degree temperature window. Then the cranes arrive. 40 mobile cranes position themselves across the construction zone, each one capable of lifting 8,000 pounds to heights of 160 feet. But lifting ice isn't like lifting steel. Ice fractures under uneven pressure. It shatters if the crane accelerates too fast. It develops internal cracks if the cable tension isn't perfectly distributed. Operators are making split-second calculations about weight distribution, swing momentum, and placement angles while working in conditions so cold that hydraulic fluid thickens and response times lag. One mistake and a 1,500-pound block becomes a fragmentation grenade. But the real challenge isn't lifting the ice. Building the impossible. The structures they're building reach 160 feet into the air. You're looking at ice towers, taller than a 15-story building, constructed with blocks that weigh over 1,000 pounds each, stacked with 0 margin for error. Engineers designed these structures on computer models that calculate stress loads, wind resistance, and temperature fluctuations down to the degree. Every single block placement is mapped out in advance because you can't tear down ice and start over. Once it's mortared, it's permanent. Here's the problem. Ice isn't a construction material. It cracks under its own weight. It expands and contracts with temperature swings. It develops structural weaknesses you can't see until catastrophic failure. So they're not just stacking blocks. They're engineering compression systems that distribute millions of pounds of weight across foundations that are themselves made of ice. The bottom blocks bear loads exceeding 3,000 psi. That's more pressure than most concrete can handle. And it gets worse. They're carving architectural details into structures while they're building them. You're watching sculptors 50 feet in the air, chiseling intricate designs into ice blocks using chainsaws and pneumatic tools, knowing that one wrong cut compromises the entire wall's integrity. They're replicating the Forbidden City's roof details, the Roman Colosseum's archways, Gothic cathedral spires with buttresses thin enough to see through. Every cut removes material and reduces structural strength, but the designs require precision down to the inch. Then comes the most insane part. They're building bridges made entirely of ice. Suspension bridges spanning over 300 feet, designed to hold the weight of hundreds of people walking across simultaneously. You're engineering tensile strength into a crystalline structure that naturally wants to shear apart under lateral stress. Steel cables freeze-bonded into ice pillars. Deck sections mortared together across massive spans. Load calculations that account for dynamic weight distribution as people move across the surface. One miscalculation, and the entire bridge collapses with hundreds of people on it. But none of this works without what they install next: the illumination system. 500,000 LED lights get embedded into the ice while the structures are still under construction, not attached to the surface, not hung from cables, frozen inside the ice itself during the building process. You're watching electrical teams drilling channels through 1,000-pound blocks, threading fiber optic cables and LED strips through passages barely an inch wide, then sealing everything with ice mortar before the block gets lifted into position. Every single light needs to be positioned, tested, and waterproofed before it disappears into a structure forever. And here's the engineering nightmare. You're running electrical systems through a material that conducts electricity when it melts. The entire power grid delivers 8 megawatts of electricity through cables embedded in ice structures, reaching 16 stories high. Engineers designed a distribution network with transformers positioned every 50 feet, circuit breakers that trigger if ice temperature rises even 2 degrees, and backup systems that reroute power if any section fails. You're preventing electrical fires in a city made of frozen water, where a single short circuit could melt support structures and bring down entire buildings. Then comes the color-changing system. Each LED can shift between 16 million color combinations, controlled by a central computer system that coordinates 500,000 individual lights simultaneously. You're programming light shows that pulse through entire city blocks, with color waves traveling across structures at precise intervals, creating effects that make solid ice appear to flow like liquid. The programming alone requires mapping every single light's 3-dimensional position in space and syncing timing down to the millisecond. But the lights generate heat, every single one of them. 500,000 points of thermal energy embedded inside structures that can't warm up without collapsing. Engineers calculated the exact wattage threshold. Each LED can't exceed 0.2 watts, or it melts the surrounding ice. That's barely enough energy to be visible in daylight, but when darkness falls and all 500,000 lights activate simultaneously, the entire city glows bright enough to be seen from space. And they're installing all of this while racing against a deadline that's already half over. Structural reinforcement. The ice can't hold itself up. Not at these heights. Not with these loads. So they're embedding steel frameworks inside the structures while they build, creating hidden skeletons that bear the real weight. You're watching welding crews assembling steel beam networks in -30-degree cold, then encasing every joint, every connection, every support column in ice blocks that make the metal invisible. The engineering specs require steel reinforcement every 12 feet vertically and every 8 feet horizontally, creating internal cages that prevent catastrophic collapse. But here's what makes it impossible. The steel and ice expand at different rates. When temperature drops 10 degrees, steel contracts by 0.006 inches per foot. Ice contracts by 0.009 inches per foot. You're bonding two materials that literally pull apart from each other as the temperature changes. Inside structures experiencing temperature swings of 20 degrees between day and night. Engineers designed expansion joints at every steel-to-ice connection point, with flexible mortaring techniques that absorb the differential movement without cracking. Get it wrong, and the entire structure fractures from the inside out. Then there's the wind loading problem. Structures reaching 160 feet tall act like sails in Harbin's winter winds that hit 40 miles per hour. You're calculating lateral forces on buildings with no foundation anchors, no deep pilings, no connection to bedrock. The entire city sits on top of frozen ground that's itself expanding and contracting. Engineers installed steel anchor cables running from the top of tall structures down through the ice into the frozen earth below, tensioned to 7,000 pounds each, creating guy wire systems that keep towers from toppling in high winds. And every single cable is invisible, frozen inside the ice. But the deadliest threat isn't wind or weight or temperature swings. Crack prevention, ice cracks. It's what ice does. Thermal stress, structural loads, vibrations from construction equipment. Everything creates fractures that propagate through crystalline structures at speeds exceeding 1,000 feet per second. You're watching hairline cracks appear in real time as workers build, spreading through blocks like lightning, compromising structural integrity before the mortar even sets. A crack starting at the base of a tower can reach the top in under 2 seconds, and once it forms, there's no stopping it. So they're monitoring every structure with thermal imaging cameras that detect temperature variations of 0.1 degrees. 30 cameras positioned across the construction site, scanning continuously, feeding data to engineers who track crack formation before it becomes visible to the human eye. Because cracks start as thermal differentials. A section of ice 0.5 degrees warmer than surrounding material creates internal stress that leads to fracture. The cameras detect these hotspots, and repair crews rush to that exact location with liquid nitrogen sprayers that instantly cool the ice back to uniform temperature, stopping crack propagation before it starts. But you can't prevent every crack, so they're engineering around them. Controlled fracture zones built into the design itself. Engineers deliberately create weak points every 16 feet vertically sections of ice, intentionally thinner than surrounding material, so when thermal stress builds up, cracks form at predetermined locations instead of randomly destroying load-bearing walls. You're watching them build failure points into structures on purpose, sacrificing controlled sections to save the entire building. The weak zones act like earthquake joints in skyscrapers, absorbing stress that would otherwise shatter critical supports. Then comes the freezing technique that shouldn't work at all. They're using flash freeze mortaring that bonds ice blocks in under 60 seconds. Water mixed with calcium chloride sprayed between blocks, creating bonds that reach full structural strength in 1 minute instead of the normal 20 minutes. You're eliminating the waiting period where thermal expansion causes misalignment, but the chemical additive changes ice properties in ways that could catastrophically fail under load. The bonds hold 3,200 pounds per square inch, stronger than the ice itself, but only if the mixture ratio is exact within 0.01%. One batch mixed wrong, and an entire wall section fails without warning. But there's something even more critical they're installing right now. The refrigeration network. Underground pipes snake through the entire construction site, pumping glycol coolant at minus 50 degrees Fahrenheit through a network spanning 12 miles. You're looking at an industrial refrigeration system powerful enough to cool 30,000 homes, redirected to keep ice structures frozen in temperatures that naturally want to melt them. Engineers buried these pipes 6 inches below the surface before construction even started, creating a frozen foundation that maintains constant temperature regardless of what's happening in the air above. The system pumps 4,000 gallons of coolant per minute through the entire grid. That's enough liquid to fill an Olympic swimming pool every 12 minutes, all of it circulating in a closed loop that removes heat from the ground faster than sunlight and body heat can add it. Temperature sensors embedded every 10 feet along the pipe network feed real-time data to a central control system that adjusts flow rates automatically. If one zone starts warming up 0.3 degrees, pumps increase coolant flow to that sector within 15 seconds, flooding the area with colder liquid before ice structures above start developing stress cracks. But here's the engineering problem nobody anticipated. The pipes themselves generate vibrations. 4,000 gallons per minute moving through 12 miles of pipe creates pressure waves that pulse through the frozen ground at 60 cycles per second. You're sending constant vibrations through foundations supporting structures that weigh millions of pounds, and vibrations cause ice to fracture. Engineers install dampening chambers every 300 feet, expansion tanks that absorb pressure spikes and smooth out flow turbulence, turning chaotic pulsing into steady circulation that doesn't shake the structures above. Then they added the emergency backup system. 40 mobile refrigeration units positioned around the perimeter, each one capable of generating 200 tons of cooling power, ready to activate if the primary system fails. These aren't small units. You're looking at industrial chillers the size of shipping containers, with backup diesel generators that can run for 72 hours straight. Because if the refrigeration network goes down for even 30 minutes during a warm day, surface ice starts melting, and structural bonds begin failing throughout the entire city. And none of this matters if they can't finish construction in the next 6 days. The speed problem. They're building structures faster than concrete skyscrapers go up. A 15-story ice tower takes 4 days from foundation to completion. That's the same time frame conventional construction uses just to pour basement footings. You're watching crews complete in 96 hours what should take 9 months. And the only reason it's possible is because they've engineered every single step to happen simultaneously instead of sequentially. 20 structures rise at the same time across the construction zone. While crane operators lift blocks on the east side, sculptors carve details on the west side. While electricians embed lights in the north sector, refrigeration teams test cooling systems in the south sector. Engineers coordinated the workflow so no crew ever waits for another crew to finish. Every team operates on independent timelines that somehow synchronize into completed buildings emerging every 72 hours. You're watching orchestrated chaos that looks random but follows precision scheduling down to the 15-minute interval. And here's what makes it insane. They're modifying designs in real time during construction. An ice block cracks during lifting? Sculptors redesign that entire wall section in under 10 minutes to work around the damaged piece. When predictions change, engineers recalculate structural reinforcement and install additional support cables before the tower reaches critical height. Temperature drops 5 degrees overnight. The entire mortaring technique changes to account for faster freeze times. You're making engineering decisions on the fly that would take conventional construction projects weeks of meetings and approvals. Then there's the material waste problem. They can't afford mistakes. Every damaged block, every miscut piece, every cracked section represents wasted time they don't have. So they built ice block sorting facilities that pre-grade every piece before it reaches construction crews. Blocks get measured, scanned for internal flaws, categorized by clarity and structural integrity, then delivered to the exact structure where they're needed. The logistics system tracks 18,000 blocks simultaneously, routing them through the construction site like a just-in-time manufacturing plant. But with 6 days left on the deadline, they're only 60% complete. The math doesn't work. 60% completion with 29% of the time remaining means they need to accelerate construction speed by a factor of 3. You can't just add more workers. The site is already at maximum crew density. You can't extend working hours. They're already running 24/7 shifts. The only option is eliminating every inefficiency, every pause, every moment of wasted motion in a construction process already operating at theoretical maximum efficiency. And that's when they deploy the technique that breaks every rule: parallel assembly. They stop building vertically and start building horizontally in sections, constructing entire wall segments flat on the ground, then lifting them into position with cranes. You're watching crews assemble 50-foot tall wall sections lying on their sides, complete with embedded lights, carved details, and structural reinforcement, then rotating the entire piece 90 degrees and hoisting it into place in one lift. What took 8 hours to build block by block now takes 90 minutes as a prefabricated panel. The crane loads are absolutely insane. You're lifting ice wall sections weighing 12,000 pounds, swinging them through the air at heights exceeding 100 feet, then setting them onto foundation points with alignment tolerances of less than half an inch. The entire wall has to mate perfectly with sections already in place, with mortaring joints lining up exactly so freeze bonding happens uniformly. 1 millimeter of misalignment, and the seam creates a structural weak point that propagates cracks through the entire building. But here's where it gets dangerous. They're lifting multiple sections simultaneously on the same structure. 4 cranes working on a single building at the same time, each one swinging 12,000-pound loads within 20 feet of each other, coordinated by radio communication and hand signals, because there's no room for error. You're orchestrating crane ballet, where collision means massive ice panels shattering in midair, raining thousands of pounds of razor-sharp fragments onto workers below. The operators are making real-time adjustments to swing speeds and rotation angles, compensating for wind gusts that change every 30 seconds. Then they discovered prefabrication makes the impossible possible. Entire archways built on the ground as single pieces, complete with structural curves that would take days to assemble block by block at height. Decorative spires carved in temperature-controlled warehouses, then transported to site and lifted into position in minutes. Bridge deck sections assembled as 100-foot-long panels, eliminating the need to build suspension bridges 1 block at a time while dangling over frozen rivers. You're compressing weeks of high-altitude precision work into ground-level fabrication that happens in parallel with everything else. The construction pace goes from impossible to absolutely unhinged. Structures that were projected to take 6 more days now complete in 3. Towers rising 20 feet per day instead of 8. Entire city blocks going from empty ground to finished buildings in 48-hour sprints. The workforce hasn't increased. The hours haven't changed. They just eliminated the single biggest bottleneck in ice construction, working at heights where every movement is slow, dangerous, and constrained by physics. And with 72 hours left before deadline, they're installing the final system. Artificial snow machines activate across the entire city, spraying 200 tons of microscopic ice crystals per hour that coat every surface. You're not looking at decoration. This is structural preservation. The snow layer reflects 90% of incoming sunlight, preventing solar radiation from heating ice surfaces by 15 degrees during the day. Without it, thermal gradients crack structures from the outside in within hours. Then comes the maintenance protocol that never stops. Crews patrol 80 city blocks 24 hours a day with handheld thermal sensors, scanning for hotspots that indicate structural stress. Any section reading more than 2 degrees warmer gets flagged immediately. Repair teams arrive within 5 minutes, carrying liquid nitrogen sprayers and pre-cut ice blocks for emergency patching. You're running continuous triage across a frozen metropolis, treating thermal injuries to buildings the same way emergency rooms treat trauma patients. And they're monitoring crack propagation in real time, with acoustic sensors embedded throughout the structures, listening for the specific frequency signature of ice fracturing at 18,000 Hz. The system triangulates crack locations within 3 feet and predicts where the next structural failure will occur before it happens. But the most critical engineering happens underground at night. When temperatures drop to minus 40 degrees, they pump heated glycol through 12 miles of refrigeration pipes, not to warm the ice, to prevent it from getting too cold. Because extreme cold makes ice brittle and prone to sudden shattering, you're maintaining temperature within a 4-degree window across the entire city, cold enough to prevent melting, warm enough to prevent fracturing, controlled by a central system, adjusting flow rates every 15 seconds. 21 days after cutting the first block from a frozen river, the city stands complete. 160 feet tall, 80 city blocks. 220,000 cubic yards of ice transformed into architectural structures that shouldn't exist. 500,000 lights embedded inside buildings, engineered to support millions of pounds of frozen water. And when darkness falls and the entire electrical grid activates simultaneously, you're looking at a glowing metropolis built in 3 weeks that most countries couldn't construct in 3 years. This is what's possible when engineering refuses to accept impossible.